Hello everyone. I'm going to talk about transit ultra-luminous X-ray source ULX4 in M51. We worked together with this group. M51 galaxy hosts large number of transit X-ray sources. One of them is well-known source ULX4. The first detection of ULX4 was reported by Tereshima and Wilson. This source, one of the 8 ULXs cataloged by Schwartz with unabsorbed luminosity. Purpose of our study, we focus on determining the nature of transit source ULX4 and its potential optical counterpart. Toward these goals, we carry out comparative spectral and temporal analysis of X-ray observations of ULX4 using the archival XMM Newton, Chandra, and Swift observations. A number of these observations have not been used in previous study of this source. In addition, we make extensive use of archival HSU observations in an effort to isolate and identify possible optical counterparts of ULX4. The source was observed multiple times with XMM Newton and Chandra Swift XRT over 20 years. This table shows log HSC observation, and the figures position of our source shows on the true color XMM Newton and Chandra images. Also, our source was observed by Swift XRT multiple times, but these observations have very different exposure and data quality. Finally, we used 82 observations with total counts greater than 0. To find models that best represent source, we applied single or two-component model with galactic absorption. Acceptable models were examined according to reduced chi-square in this range and F-test. This table shows X-ray spectral fitting parameters of ULX4 obtained from power law and power law plus Mekal model. The best fits power law model obtains Chandra, while power law plus Mekal model obtained from XMM data. We noticed that flux values of the source varies by factor of 200. In there, left and right panel show unfolded energy spectra from Chandra and XMM Newton data. Also, to indicate the possibility of correlation between luminosity and photon index, we determined Spearman rank correlation coefficient. The magnitude of the coefficient is too small, suggests any significant correlation. To search short-term count rate variability, X-ray light curves of ULX4 were bined over different time intervals in this energy range. However, no variability was detected. In addition, to search for an underlying pulsar, XMM Newton and Chandra datasets were used to perform timing analysis. For this X-ray light curve sample, 0.1 second, yielding 5 Nyquist frequency, were Fourier transform to generate power density spectra. However, no signal stronger than 1.5 sigma confidence levels detected. We also performed long-term variability of ULX4 by deploying the more recent data. The black, blue, and red symbols represent Chandra, XMM, and XRT observation, respectively. Also, dash black line shows ultraluminous states. In this figure, right panel shows its histogram. We find some evidence bimodal distribution in Chandra data. However, bimodality feature is not evident either XMM or Chandra data. Bimodality give us important information. Bimodality feature is present, then it may be indicative of disk or precession. The Propel effect, which requires the neutron star to have a very strong magnetic field, and other possibility, for example, binary stem, is which neutron star is typically in a moderately eccentric orbit, and the change in the accretion rate via follow separation as the system transition from the high to low state. Focusing more on the long-term spectral evolution of ULX4, we note the recent study of Gurpide et al., in which they present hardness luminosity diagram for a sample of 70 ULX, including pulsar ULX, with archival data from Chandra, XMM, and NuStar data. ULX4 occupies the lower section of the luminosity. The dashed line indicates luminosity level. However, according to finding of Gurpide et al., the majority of the confirmed pulsar ULX reside in the region corresponding to higher luminosity and higher hardness. These would tend to suggest that compact object in ULX4 is either stellar black hole or a neutron star with a low magnetic field. And the primary aim of the color diagram introduced by Don Grilensky, it is to map the spectral transition and, if possible, identify the nature of the compact object from the tracks they follow the respective domains. Our source consistent with Don Grilensky for a sample of galactic black hole transients whose spectra are well described by power law. ULX4 is more likely to be transit black hole than neutron star. In time lags, ULX4 indicates a relatively high degree of variability based on the hardness intensity diagram. We have attempted extraction of the frequency-dependent time lags following the pressure outlined Utley and Pintor et al. We used background subtracted Chandra light curve in this energy range, also for other following bands. However, the weighted spectral lags are consistent with the zero within the error bars for both sets on the energy band. We used HST data for properties of optical counterparts ULX4. This table shows log of optical observations. To find optical counterparts, we match Chandra and HST image, and we find 3 reference sources. We use these reference sources. We derived asymmetric error radius as 0.80 arc seconds. In this error radius, we find two optical counterparts shown in this figure with white bars. We labeled A and B. We performed PSA photometry and we derived Vega magnitudes, UV to infrared bands. When we compare other optical counterparts, our optical counterparts faint sources. Using this value, we obtain spectral energy distribution.
Sinan, may I ask you to sum up in a minute?
Sorry?
May I ask you to wrap together in a minute?
Yes. Okay. Spectral types of counterparts A and B were estimated two different ways. The first used the Castelli-Kurz models, indicated both comprehensive early B-type supergeon. As part of the same procedure, we identified spectral types of two nearby fields, R1 and R2. And second one, we made use spectral fields blackbody function in lower panel. We found this temperature, and this temperature indicates early B-type star. In order to search for periodic modulation, we constructed long-term light curve. We used the 30 HST observation with the same exposure time. One of our more intriguing results is that the optical counterpart A appears to exhibit a low amplitude periodic modulation of 264 days, although it appears only in one filter, the visible filter. We consider two possibilities for this apparent periodicity. This is our light curve and our sinusoidal fits. This function obtained from Liu et al. One involves the nature of the donor and the other about the nature of the periodicity itself. Unfortunately, in this case, donor star cannot be B-type supergeon, since such a star is not likely to fill in its Roche law, assuming the periodicity is a result of the orbital period of several hundred days. Our result with 3 sigma confidence level. Yes, I read one. And finally, the majority of X-ray data are the best described by simple power law within photon index, this photon index. A couple of XMM Newton observations indicate presence of the soft component, which best described with addition of the mechanical component, suggesting contribution from diffuse background source. We find some evidence for the existence of bimodal distribution of the X-ray flux of ULX4, the cause of which is of some debate in literature. Hardness intensity diagram and color diagram, along with the significant variability, not a long-term X-ray light curve from Chandra, present a rather mixed picture as to the nature of ULX4. For example, arguments could be evidence for either a stellar-sized black hole or low magnetic fields neutron star. We have identified two optical counterparts. Counterparts exhibit low amplitude optical periodicity, 264 days, visible filter. No periodicity was found for other counterpart. Based on the optical spectral energy distribution, spectral type in range early B type, if we assume apparent periodicity seen optical counterpart A is associated with the orbital motion of the donor, then the donor is more likely red supergiant in order to satisfy the long periodicity and the needs to accommodate Roche-Loeb overlap. As a consequence, the ACD would then have to be interpreted as a superposition of emission from cold donor, and a hot flow components, most likely from the accretion disk. If one of the other hand, the periodicity is superorbital in nature, for example, due to interactions of the compact object with the circumvented disk, then the donor could be BX star, with compact object being neutron star. Thank you for your attention.
Thank you, Sinan. If there is any, we can take one quick question. I see none. So thank you again.